Okay, we are recording now. So lab 2 is about plate tectonics. It's a two-part lab that will be occurring this week and next week. This is material that you have, I believe, covered before in lecture, and that you might have potentially had before in lecture, but I'll be doing a brief overview of plate tectonics to give you some context, because it is really the fundamental theory of geology, and it is something you need to have a good understanding of if you're going to have more than a trivial understanding of igneous rocks or sedimentary rocks or other bits of geology. It's hard to escape it. So I'm going to start out actually by giving you a very brief summary of some of the important physical layers of the Earth. So something interesting about how the Earth is divided is that the Earth is made of different layers, and we can define those layers differently depending on whether we want to talk about the chemistry, like how much silica is in the different layers versus how much iron is in the different layers. But we can also define them based on the physics. And when I say the physics, I mean whether a layer of the Earth is solid, or whether it's liquid, or if it's a solid, how it behaves. And one thing to remember is that solids are going to behave differently under stress. A hard rock or a brick, if you pull it hard enough or smash it, it's going to bend until it can't break anymore, and then it will break. But then some solids don't do this. More plasticky solids like silly putty or butter kind of deform under pressure. And something you might notice is that the warmer something like butter is, the more easily it deforms. And rocks can actually deform if they get warm enough. If they're not quite warm enough to melt and turn into magma, they can deform plastically. So the uppermost layers in terms of physics of the Earth are the lithosphere, which is a solid that behaves rigidly like solid rock, and the asthenosphere, which is a solid that's kind of deformable and capable of flow. And the lithosphere is actually the part of the Earth that the plates in plate tectonics are in. It's the crust as well as the very uppermost part of the mantle. And crust and mantle are layers of the Earth that are defined in terms of chemistry, not physics. But I'm just introducing this to give you a sense of this is where the plates actually are. The plates are in this upper rigid part, and they kind of flow over the more ductile plastic part. So the lithosphere is kind of like pond scum floating on top, and it consists of the crust, which is defined chemically by having so much silica. The crust is the outermost layer of the Earth. It's the thinnest. It's honestly quite thin compared to the rest of the layers. And it's what we're walking on. It's also what underlies the ocean floor. So there's actually two slightly different types of crust that are different in terms of how thick they are, their chemistry, their density. There's the crust found under the ocean, oceanic crust, and that which makes up the continents that we're walking on, or continental crust. Something that I find kind of interesting is that the oceans, as I'll indicate when we get to divergent plate boundaries, actually end up where the oceanic crust is and not the other way around. But the crust is joined to the uppermost part of the mantle, and that's the lithosphere. And the lithosphere is is again a physical layer. Something that I found very confusing as an intro geology student is that there's the mantle and the crust, and then there's the lithosphere and the asthenosphere. You kind of have to just know which system you're dealing with, whether you're talking about the chemistry or whether you're talking about the physics. So lithosphere and asthenosphere are all about physics, and that really is what leads us into plate tectonics, because the plates that actually give plate tectonics their name are in the lithosphere. They're the upper rigid part, and they're basically floating over the asthenosphere, the weak, still solid, but kind of plasticky part. Questions so far? Okay. So what is plate tectonics? Plate tectonics is the theory that the Earth has a surface that is broken into rigid plates, and that these plates move on the flowing asthenosphere underneath, and that these plates move relative to one another. And plate tectonics states that earthquakes, the vast majority of earthquakes, volcanoes, and other geologic processes can be explained by this movement or somehow linked to it. So The interesting thing about plate tectonics is that it's a pretty young theory. My grandma is 79 years old, and she went to college and took a geology class before plate tectonics was an established theory, which I find kind of fascinating. It's been around less long than the theory of evolution. And the theory of plate tectonics actually came about through what I think are some common sense observations. We know a lot now about what the Earth is like inside chemically and physically, but that's a pretty recent development. And before anyone really even knew about that, the idea that the Earth's surface could move at all was a new idea even in the 1800s. So that also is a relatively recent development, and that's kind of what came first, this theory of continental drift, that the continents are not presently, where the continents are presently located is not where they've always been. And there were a number of people who worked on this theory, but the person to publish the theory of continental drift first was an Austrian scientist named Alfred Wegener. And what I kind of find interesting about the story is that a lot of his observations feel like things that I noticed when I was like a kid fascinated with maps, or just someone interested in dinosaurs. So the 1800s were when they were first finding tons of fossils, and they were finding fossils of land animals in both Africa and South America, so separated by the Atlantic Ocean, but the same exact fossil found on different continents. They were also finding dinosaurs as well as mammal ancestor fossils in Antarctica and India and South and Africa, all of the same creature. And for one thing, none of those continents are anywhere near each other today. For another thing, Antarctica doesn't really support much life today, but they found giant fossils from there. So that indicated that the continents had moved. Also, the thing that I find kind of cute is that he and the other scientists basically looked at maps of the world, and they noticed instances such as the fact that the eastern coastline of South America, where Brazil is, and the western coast of Africa kind of look like they should fit together. And in fact, they do, because at one point they were joined. They've been separated by plate tectonics since when they were joined, but this was even before anyone knew about plate tectonics or knew what was driving it. They also found glaciers in places like South America and Africa that had clearly been at sea level. So it indicated those continents had moved and been at latitudes where you get glaciers. And then they also just found geologic structures on either side of the ocean that looked exactly the same. And one thing to note here is that this is a map where you can actually see the mid-ocean ridges. This shows a lot of the same features that you saw in the underwater map that you looked at last week. People didn't know any of this was here yet. The idea of continental drift was thrown out for a long time because there was basically no mechanism that he could come up with to explain it. And this was actually before the mid-ocean ridge was discovered. So the mid-ocean ridge is an underwater volcano, and it's actually a plate boundary. It's primarily a divergent plate boundary, which is one of the types of plate boundaries we'll learn about. But what is happening at the mid-ocean ridge, like the one under the Atlantic Ocean, is that a volcano is erupting at the center and producing new oceanic crust, and that crust is spreading outward. What is known as seafloor spreading is happening. And this was not observed until the early 20th century, when sonar and submarine technology actually allowed people to see what was underwater and realize that the ocean floor wasn't just this completely featureless expanse, that there was in fact what is basically a long underwater volcano actually running all the way from Antarctica to Iceland and producing new crust and causing the crust to move outward. It was the first indication that, okay, we can actually kind of see Earth's crust moving in a sense. And I have an animation here that was actually made by an emeritus professor at UCSB, Dr. Tanya Atwater. If you're interested in these, I can link you to the website where you can download these, because I find these animations very useful for plate tectonics. But This is an animation of what's actually happening at a mid-ocean ridge, what's happening with seafloor spreading. So what's this orange stuff? Can someone tell me that?
Magma?
Is it lava or magma?
Oops. Yes. Yes, correct, Jeanette. It is indeed magma. It is molten rock. So this is actually what I mean when I say that the mid-ocean ridge is a volcano. There's this long fissure through which magma is erupting. And this segment here is known as a divergent plate boundary because you can see the magma is erupting, forming new crust, and the plates are moving in opposite directions. So a mid-ocean ridge is dominated by divergent plate boundaries where the crust is moving in opposite directions. And it was the discovery of these plate boundaries that actually enabled the discovery of plate tectonics. Something I want to mention briefly, not super important for this lab, is one reason that they were even able to figure out that was happening, because that was a in terms of people not being able to hear me, I believe that you should be able to unmute yourselves, but if that is not the case, I will fix that afterwards. If people have been saying things into the microphone, I haven't been able to hear anything, which is probably not good, but I will deal with that in a moment. So chat might be easier if you want to ask questions. I don't mean to be ignoring anyone. It sounds like I might have missed some questions. So I will actually very briefly pause to give people a chance to type questions that they might have been missing earlier, because I'm not quite sure why I'm not able to hear anybody. So I'll give people a second to ask questions before I move on with the presentation. Mute, select a speaker. Speakers 3. Okay, can someone try saying something now?
Hello?
I can hear you now. So what happened literally is that my cat at one point sat on my keyboard and pushed the mute button without me noticing. That is literally what happened. My frigging cat sat on the mute button and I didn't notice. So I am very, very sorry about that. I am really sorry if it seems like I've just been ignoring you. This little lady sat on the mute button.
No, we kind of figured that something was wrong because some questions came up and there was just a blank stare.
Yeah, I wasn't trying to ignore people. So I can take a brief pause for questions. We've kind of reached like introduction of plate tectonics. I'm going to start going over plate boundary types next, but pause for questions now that the sound is behaving. Okay, doesn't seem like there's any that come up. I will keep my eye on the chat, and thank you for helping me troubleshoot that. I was really wondering why I couldn't hear anybody. So that makes me feel better. Okay, anyhow, so this point here is not, this point here is a little bit of evidence about how they actually came up with this model, because the animation I showed on the last slide is a very sped up version of what's happening. You can see that it's erupting if you go to the mid-ocean ridge, but seafloor spreading happens very slowly. But one bit of evidence they had was that Earth has a magnetic field. There's little bits of iron in the magma that will point in a certain direction based on what Earth's magnetic field is like at a given time. And something you may know about already is that Earth's magnetic field switches periodically. And when that happens, it causes the iron specks in the magma to point in the other direction. The cool thing is that when the magma cools into rock, it actually gets preserved. That which direction the iron is pointing in gets preserved. And so you can look at the rock and actually figure out what direction the Earth's magnetic field was pointing at the time. And what they find is that on either side of the mid-ocean ridge where the magma is erupting, there's a symmetric pattern. You go from regular to reversed and then to regular going outward. And there's another variation of the animation on the next slide that kind of shows you what I mean. In this version, they've colored the seafloor to show that when it's erupting, it's one type. During this long stretch here, I'm going to go back. So right now it's erupting normal. And then when Earth's magnetic field shifts, they color it black. And you'll see that there's a little stripe on either side. It was a pretty brief shift, but it's reflected on either side symmetrically. So this model is actually what they've observed when they look at the magnetism of the rocks on the seafloor, which is pretty darn cool. But another bit of evidence actually has to do with looking at how old the rocks are, what's called radioactive dating, because the ocean floor rocks, since they're volcanic, they have minerals in them where they can actually measure the radioactivity in the minerals and see how long it's been since they were erupted. And what that's done is they've been able to find that the youngest rocks are close to the center of the system, like at the mid-ocean ridge itself. And as you go farther and farther out, you have older and older and older rock. So here's a question. When you get farther and farther away from the mid-ocean ridge, so at the mid-ocean ridge itself, you have the eruption, you have seafloor spreading. Which crust is going to be, is older crust going to be colder or is it going to be warmer? That's the question I want to start with.
Warmer?
Older crust. So think about what it's like when it's young. When it's young, it's first being erupted at the volcano.
So it's going to be colder?
Yes, colder. Yes, precisely. It's going to be colder because it's going to be longer and longer since it was a molten liquid. What's happening? I'm going to very briefly jump back to the animation, but what's happening is that you have warm magma gets cooled into rock, and that rock is going to get colder and colder and colder as it just sits on the seafloor, and it's been longer and longer since it was a magma to begin with. So the interesting thing is that the rock that was magma more recently is warmer because it hasn't had as much time to cool. It's kind of like if you leave like hot cookies out. They're solid. They were kind of liquidy to begin with. Then when you take them out, they cool, and they're going to get harder and harder and stiffer as they sit there for longer. And that's one reason that why people compare crust to using baking analogies a lot. Also, the word crust shows up also, which I think is kind of cute. But the second question, is the crust going to get more or less dense as you get farther and farther out from the mid-ocean ridge? We're talking about the crust on the ocean floor itself.
More dense?
More dense?
Yep, more dense, because the colder it gets, the more dense it actually is. Cool. So the takeaway from this is that we have symmetrically older and older rocks on either side, and the rocks are cooler and denser on either side as well. And in this color scheme, you can actually see that they intentionally chose red for the youngest rock at the mid-ocean ridge itself, and then the blue represents the oldest oceanic crust, which is not actually that old. The oldest ocean rocks we have are only 200 million years old, which sounds like a lot, but there are dinosaur species that lived before that. So what happens to all this oceanic crust? That is where we get subduction. And subduction was another discovery that helped confirm the theory of plate tectonics, because there needed to be some explanation for where all this oceanic crust was ending up if the Earth wasn't just going to keep getting bigger and bigger. And what actually happens is that it sinks into the mantle when oceanic crust meets continental crust. It turns out oceanic crust sinks into the mantle, and when you have plates that are made of ocean crust going in different directions, coming towards each other that meet, whichever one is denser is going to subduct. And that's one reason why I had you think about the density of oceanic crust, because there are some instances where you have tectonic plates composed of oceanic crust coming together, and one of them will indeed sink into the mantle, be subducted and recycled and subduct. If you've heard about trenches like the Marianas Trench, that's actually what's happening there. Trenches are where subduction is occurring. And trenches are extremely geologically active places because, for one thing, when you have one plate going back into the mantle, it's going to cause earthquakes. That's going to cause a lot of stress, which is going to cause earthquakes. And it also brings melting that causes volcanism. Trenches like the Marianas Trench or the trench you have off the coast of the Pacific Northwest, those are associated with arcs of volcanoes. And here's where something related to the lab here's where I have a map that is similar to one you're going to see in lab today, actually. When scientists were working on the theory of plate tectonics, one important bit of evidence was that as they started finding the locations of spreading centers as well as trenches where crust was being subducted, they mapped where earthquakes were occurring, and they found that earthquakes, to a big extent, corresponded with these places that, as we now know, are actually plate boundaries. So spreading centers are plate boundaries. Subduction zones are plate boundaries. And those plate boundaries, it turns out, are where there are tons of earthquakes. The biggest earthquakes tend to actually occur at subduction zones. So where is one particular place? Do people know, so does anyone notice a particular place where it's really dense with earthquakes that catches their eye?
Ridgecrest?
Yeah, Ridgecrest.
Sorry, can you say that again?
Said Ridgecrest.
Ridgecrest earthquake. Great. So that wasn't the question I was asking exactly, but the Ridgecrest earthquake is actually a really good example of an earthquake caused by a transform fault. That's one near where you all live, and that was an earthquake along not the San Andreas Fault itself, but along one of the little faults that exists alongside it. That something we don't really talk about in this class, but when you have a fault, there's going to be one large fault, and there's often going to be little faults running parallel to it that are kind of affected by the same stress. But if you can actually see that there's a thick belt of earthquakes kind of encompassing where Ridgecrest is. Ridgecrest is going to be somewhere in this belt of earthquakes. And the funny thing is that the California earthquakes are one instance that are not actually caused by a subduction zone. They're caused by a transform boundary, which is the type of boundary where you have crust moving in opposite directions on land. And I'll talk about transform boundaries in a bit. But you can see there's a lot of earthquakes there. That's one of the few examples on this map where it's not directly related to subduction. Where is another place where you see a big concentration of earthquakes? Like where you see just a sea of green?
By Japan.
By Japan. And Japan is a great example of a place where one oceanic plate is actually going under another oceanic plate. The islands of Japan are formed by volcanoes that formed from subduction that's occurring out in the ocean, and there's a lot of earthquakes occurring from that subduction. An example of where you have oceanic plates going under a continent is on the west coast of South America. So there are always big earthquakes in Chile and Argentina and Peru, and that's from the oceanic crust of this plate over here is the Nazca plate, and that is subducting under the South American plate, and that's actually what the Andes Mountains are also from. So in general, most earthquakes occur at plate boundaries. There are some exceptions. You can see there's a scattered number of ones in the middle of the United States, far from any plate boundaries. And there are other reasons earthquakes can occur. Fracking can cause earthquakes. Earthquakes can sometimes occur along dead faults. Also, I'll mention there is one type of volcano that doesn't occur at a plate boundary, a hotspot, and that can also cause earthquakes too. So there are earthquakes in Hawaii sometimes from the movement of the magma under the hotspot, but in general, you get earthquakes at plate boundaries. What about along the mid-ocean ridge? Is it a really thick concentration of green dots compared to, say, Japan or the western coast of South America?
It's relatively thinner.
It's relatively thinner, right. And that actually has a lot to do with how warm the crust is at the mid-ocean ridge. Because at the mid-ocean ridge, you have crust that has just cooled. It's pretty young and warm, and it's under constant stress, but since it's still pretty warm, it's not quite as brittle, and you get lots of little earthquakes relieving the stress. You get the big earthquakes with subduction because that's cold rock that is really brittle, and that tends to build up a lot of stress when it's grinding against another plate. And then this is the map of the volcanoes, so it's similar. And this one has the plate boundaries already drawn in, you can see. But one thing is that they don't really seem to consider the mid-ocean ridge an active volcano because it's kind of low-level volcanism, and I do find that a little bit misleading. But you can see that there's volcanoes in some of the places we mentioned before, like the islands of Japan exist completely because volcanoes have erupted and produced volcanic rocks that make up those islands. And a lot of Western North America, like in the Cascades and southern southeastern Canada, there's volcanoes there caused by subduction. Interesting thing about California is that you have volcanoes more in the northern part of the state, and that's caused by subduction occurring off the coast of Vancouver Island in British Columbia. The Sierra Nevada are related to volcanism that recently occurred farther south, like a little closer to where we are, but the San Andreas Fault has kind of replaced that, which is interesting. The San Andreas Fault has kind of taken over a subduction zone that used to occur here, but that's kind of an extra note. Questions? But you're going to be using a similar map in lab. It's not this exact same map, but you're going to be referencing two maps that are they're uploaded on Canvas. They're listed as links in Canvas itself at the top of the assignment itself. And I'm briefly going to jump out of PowerPoint to just show you what those look like. So I should still be on the screen share. So this is the volcano map that you'll be using, and you'll notice that this doesn't have plate boundaries marked in it. This kind of gives you a chance to, when you get to this exercise in lab, this kind of gives you a chance to look to, in your head, compare plate boundary maps you've seen and think about, okay, how does where these volcanoes are located line up with that? Like, should we expect plate boundaries here? And you can kind of see the mid-ocean ridge. Actually, Iceland is a really good example of a volcano caused by the mid-ocean ridge. Iceland is geologically very weird, but you can see there is a small chain of volcanoes running down the Atlantic. So you can see that there's volcanism at mid-ocean ridges also. But this map you can download on Canvas, through Canvas. It's a PDF. I didn't have any trouble opening it, but I will say that the earthquakes map, I found a little bit sluggish. I think it's just because it's a large file with a bunch of different layers in it. If anyone has trouble opening this, I can export this as a JPEG and upload that. And I will probably just go ahead and do that once I finish with this presentation, because I discovered that while I was looking through this. But this map shows earthquake locations, and with the earthquakes, you can see it even more clearly. You can see that there's a non-trivial but kind of lots of sort of low-level earthquakes happening at the mid-ocean ridges, and then you can see tons of earthquakes occurring in places like Japan or the Mediterranean Sea, where there's subduction occurring, and that's what caused Mount Vesuvius, actually. Mount Vesuvius, which destroyed Pompeii, was a volcano caused by subduction, or Indonesia, or off the coast of South America. And so having kind of taught plate tectonics before, I see this and I can kind of see where the plate boundaries are even without them being explicitly marked as such. And that's something you'll kind of, the more you look at maps like this, that'll kind of stick out more, the more that you see plate boundary maps. But I'm very happy to walk you through this as you're working on it. But this is the earthquakes map that the lab actually talks about. Does anybody have, and the colors refer to intensity of earthquakes. You don't really have to worry about that much, but it's just kind of cool to see where the most intense earthquakes are occurring. Does anybody have questions about either this map, the earthquakes map, or the volcanoes map before I jump back to the PowerPoint? Okay, that sounds like a no. So let me jump back into PowerPoint, and I will talk about this figure in just a moment, or in just a bit. Oops. And time for one more animation in here. This is actually what happened to the Atlantic Ocean. The Atlantic Ocean formed from seafloor spreading. All of that information, like the shape of the continents fitting together and fossils being found both over here and over here. It turned out that the Atlantic was not existent at one point, that it that a spreading center formed and pushed the continents apart over time by making new oceanic crust. So let's talk about plate boundary types. Subduction and seafloor spreading occur at different types of plate boundaries. A divergent plate boundary is where two plates are moving away from one another, and that's seafloor spreading. A convergent plate boundary is when you have two plates coming together, and that either makes subduction, or if you have two continents colliding, that creates continental collision. And look at the arrows in this diagram. The arrows give you a clue as to what kinds of plate boundaries we have here. Does anyone, so a convergent plate boundary would be likely you'd see two arrows coming together. Can anyone see an example of where you have a convergent boundary where there's two continents together? Where the plate boundary is on land and there's a convergent plate boundary, where there's two arrows coming together?
The Pacific Plate.
The Pacific Plate, and what other plate are you referring to?
The Australian plate?
Yeah, the Australian Plate and the Pacific Plate. Thank you.
That is a really good example. That is that's an example of a convergent boundary where you have oceanic crust in the Australian plate and oceanic crust in the Pacific plate. So actually there is subduction there. There is subduction producing the islands of Melanesia, like the Solomon Islands and Vanuatu, are being produced by that. But I apologize for not being more clear. I was referring to an example of one on land. And what was that I just heard?
Asia?
Where in Asia?
No. Oh my gosh. Southern Asia. Oh, you mean like which?
Like where on this map do you see a convergent boundary on land? Like two arrows approaching each other on land.
Where the yellow and the purpley brown meet.
Where's
the Eurasian Plate and the Indian Plate?
The Eurasian plate and the Indian plate is the example I was looking for. Yes,
cool.
And that's actually one of the only examples occurring. But that is where two plates are undergoing continental collision. So what's between India and Tibet? What geographic feature?
Is it
The Himalayas?
The Himalayas. The Himalayas. Yes, that's where Mount Everest is. Those mountains are so high because they're being produced by two continents colliding. And I'll talk about that. But when you have two continents meet, that produces really huge mountains, like we have in the Himalaya today. The third type of plate boundary is a transform boundary. And divergent, they're going to show two arrows going apart. Convergent, they're going to show them going together. They will normally show transform kind of going in, like one arrow goes up, one arrow goes down like this. There is only one example that you can see on this map. Where is that?
Is it the Caribbean Sea and the Cocos Plate?
That is an example of a convergent boundary, actually. I'll give you a hint. It's not far from where we are.
Yeah, I see it right.
Can you describe it to me?
It's like off of the coast where we're at.
Yes,
pretty much.
precisely. That is the San Andreas Fault. This is a transform boundary. And the interesting thing about transform boundaries is they normally exist as these tiny connector segments in mid-ocean ridges. The San Andreas Fault is kind of a gigantic example of that, and one of the only cases where this movement, the sort of side-to-side movement, is happening on land. And there's some other terms I have in here that might come up. I'll introduce them as they come along. But these are the three actual types of plate boundaries. These are the actual three types of places where the crust moves. So divergent plate boundaries are seafloor spreading. And the interesting thing is that seafloor spreading does not actually usually begin on land. People know Death Valley, right? Death Valley is a really good example of what at one point was a divergent plate boundary, and it would have become an ocean if seafloor spreading had occurred long enough. And I say seafloor spreading even though it's on land because confusingly divergent plate boundaries often form on land and then push the continents out far enough that the ocean can flow in, which is actually what happened with South America and Africa. But something really interesting that's going on in Eastern Africa right now. You might have noticed on the Volcanoes map that there were a lot of volcanoes in Eastern Africa, like in the interior of the continent, like in Ethiopia and Kenya and Tanzania and near the African Great Lakes. And actually the African Great Lakes are there because that is really low down. It's called a rift valley because it's a divergent plate boundary. It is where oceanic crust is actually erupting on land, and it's pushing the continental crust to either side, and it's kind of causing the crust to drop down. And it hasn't dropped down enough in Eastern Africa or done this continuously enough that the ocean has been able to flood in yet, but the lakes are there because it's so low down and the water flows down there. And if this process continues, what will happen is stage 3 in this diagram. It will actually get low enough for an ocean to flood in, and there will eventually, if this goes on long enough, be a new larger ocean between Eastern Africa and the rest of the continent. So the Great Rift Valley in Africa is a really good example of how divergent boundaries and seafloor spreading actually often start on land, and then the ocean kind of follows once the crust actually drops down enough. Oceanic crust is denser and tends to sink into the crust more than continental crust, so that's part of why this happens. I'm only going to briefly mention this, but a term that you may want to be familiar with going forward is a passive margin. In cases like the Atlantic Ocean, where you have a plate boundary out in the middle of the ocean and the continents have been pushed away for a long time, the term passive margin refers to the coastline. The term passive margin refers to the coastline that is now miles and miles away from the mid-ocean spreading center. So that's actually one reason why the eastern United States is very low on earthquakes and doesn't really have any active volcanoes, because it's not a plate boundary right now. The plate boundary is out in the middle of the Atlantic Ocean where seafloor spreading is still occurring. But North America and Eastern North America and Western Europe have been pushed apart for so long that the actual coastline isn't a plate boundary itself. It's far from the actual plate boundary, and you don't really get any earthquakes in the eastern United States as a result of that. And ignore that note about Antarctica. That's from another class I taught. But a brief summary of what oceanic crust is like versus continental crust. Oceanic crust is going to be relatively rich in iron, darker, and it's going to be referred to as mafic. And the term mafic actually comes from magnesium and Fe, or iron. So mafic refers to a rock that has, relatively speaking, a lot of iron and magnesium in it, and that makes it dark overall. It's going to be more dense, and it is formed at the spreading centers like we've been talking about. And it being so dense is what actually allows it to sink down and subduct. Continental crust is actually not able to subduct. The continental crust is usually actually formed by subduction. Subduction creates volcanoes, and that volcano that volcanism creates continental crust. The crust that we walk on overall looks a lot like this. And what is this rock? Just your first guess.
Granite?
Yes, just like, yeah, this is granite. And granite is actually what makes up most of the continents we're walking on, and granite cannot subduct. Granite is light colored because it has so much silica in it, and silica is a lot less dense than iron and magnesium. So fundamentally, this is why the crust that is underneath the continents can't subduct, and this is why oceanic crust goes under continental crust and not the other way around. And as we'll find out, why when you have two plates that have continental crust, why they will just build mountains instead of one of them subducting. So the interesting thing about the continents is that they never disappear, in a sense. The continents can't be subducted, not easily. And so on land, on the continents, we actually have rocks that are billions of years old in some cases because they haven't been subducted. And that's why, anyway, sorry, got a little sidetracked there. So time for questions. So I bring up the difference between continental and oceanic because you get subduction if you have an oceanic plate meeting a continental plate, excuse me, sorry, it's been a long couple days. You get subduction if you have an oceanic plate meeting an oceanic plate. So that's like the occurrence that some of you observed occurring in the ocean between Australia and the Pacific Ocean, or which is happening in Japan. But this is what happens when you have two plates made of continental crust coming together. Usually what happens is that there will be, like what happened with India and the rest of Asia is that India used to be a completely separate continent. It came closer and closer to Asia, and there was an ocean between them, and the ocean crust got subducted, but when the ocean was all used up, the crust that makes up India could not be subducted, and the two continents just got pushed closer and closer together, and mountains rose up as a result of that. So the world's highest mountains often exist as a result of that. And this is kind of a side profile of what's actually happening with subduction. Subduction makes magma. Subduction actually causes this mantle to melt, and that makes the magma that produces the granites that you have underground, as well as the lavas in the eruptions that you have making the volcanoes themselves. So this is kind of what we have off of the northernmost part of California and British Columbia, where you have the Cascades, where you have an oceanic plate subducting, and inland that causes magma to melt and makes volcanoes like the ones you have in Canada and Oregon and Washington and Northern California, but not so much here because we are south of where this is occurring. And I'm not going to linger on this too long, but things you find in subduction zones are trenches, and then you also will find an arc of volcanoes. So I'm going to actually jump back to the slide. What do you notice? About, you can only really see the magma coming up here, but what do you notice about where smoke is coming out along this volcano chain? Is it coming out of just one volcano, or is it coming out of all of them?
All of them.
Yep, it's coming out of all of them because this is what's known as a volcanic arc. You have this trench running along the coast, and subduction is occurring all along that trench. So you have volcanoes occurring all along that. And that's why at convergent plate boundaries, you'll see a bunch of volcanoes all along the boundary because subduction is occurring on a line. And that's a big difference to what you see in a place like Hawaii, which is a hot spot where there's just one active volcano now. So subduction zones have trenches, they have volcanic arcs, and they also have earthquakes. Some of the biggest earthquakes come from subduction happening. Or in general, convergent plate boundaries are associated with big earthquakes. You also have enormous earthquakes in Nepal, like the one that completely devastated the capital of Kathmandu a couple years ago, because this continental collision is still occurring and causing the mountains to rise higher as we speak. And there are still massive earthquakes occurring from all of that stress building up in that thick continental crust. The last type of plate boundary that I want to linger on is a transform plate boundary. And the interesting thing about transform boundaries is that, with the exception of the San Andreas Fault, for the most part, they are really small. You'll see this is kind of the same, this looks like the same animation I was showing before. And I mentioned that these segments where the magma is being produced, these are the divergent plate boundaries. This is the mid-ocean ridge, and you see that there's arrows showing that the crust on this side is moving to one's left, and the crust on this side of the segment is moving to the right. Now, you'll see how there's multiple segments. There's multiple segments that are kind of staggered, and there's these little horizontal parts that connect the segments. Jumping back a second, what do you notice about the direction of the arrows on either side of this crack? This crack that's connecting this segment and this segment in the front.
They're pulling away from each other?
They're pulling away from each other, but they're kind of going in opposite directions, like one lane of traffic going northbound and one lane of traffic going northbound. It's not subducting, and they're not going in completely opposite directions, but they're sort of traveling alongside each other. And that's what a transform plate boundary is. A transform plate boundary is where crust moves in opposite directions, but it doesn't really move vertically at all. It doesn't sink down, it doesn't subduct, and there's actually no there's not any new crust that's either made or recycled along here, nor is there any volcanism. There's volcanoes here at the spreading center. This is the divergent plate boundary. But on these little connector segments, there is no volcanism being made. Now, most of the time, this is what transform boundaries are limited to, these little connector segments between the actual spreading center segments on mid-ocean ridges. And this is why you only saw the one example on the map earlier, because the San Andreas Fault is a gigantic example of this. And it does actually connect ocean spreading center segments that are located in the Gulf of California, south of us, as well as the ones located north. But it's an instance of this, like this normally really tiny segment actually cutting across land. And I'm going to jump out of here for a second and kind of show you what I mean by that. And I'm kind of kicking myself for not putting that slide directly in here. But give me a quick second to bring this up. Does anybody have any questions while I bring the San Andreas Fault map up? Hopefully people can, oh, I can hear people again, that's good.
What about bedrock, or like how is that like affected?
You said something about bedrock. What was the rest of your question?
How is that like affected or anything? Like, does that have anything to do with it? Or?
So bedrock is a general term that refers to like whatever in a particular area you're interested in, what the rock underneath is. So bedrock doesn't refer to a specific chemical type of rock, like it doesn't necessarily refer to oceanic or chemical crust, but in practice, bedrock is going to usually be, it's usually going to be something like granite or whatever is underlying where you are, or if you're in an area that mostly used to be, or if you're in an area that has a lot of sediments, whether there's a lot of sandstone, it'll be sandstone. Bedrock basically is just a term for like what the particular rock in your area is, like what the predominant rock type is. So it can actually refer to different types of rock. Does that help at all? You might sometimes in geologic literature come across the term country rock, and that's actually the same thing. It's not a genre of music. It refers to kind of the rock that makes up most of the surrounding area you're interested in. And geologists will often use that because they'll be interested in some fossils or some small deposits of a rock that occur within the country rock, and they'll refer to the country rock as just kind of the surrounding stuff. Does that help at all?
Yeah, thank you.
Okay, cool. Any other questions before I go through the San Andreas Fault diagram? So this is a diagram that you'll actually see in your lab. There's a couple of questions near the end based on this, but this is the San Andreas Fault, and you can see that it shows that the Pacific plate is moving north and the North American plate is moving, or the Pacific plate is, I guess, going more northeast, and the North American plate is going to the, or northwest and southeast, sorry, but you get the idea. And neither plate, the plates aren't moving up or down relative to one another. They're staying at the same level, but they're just kind of sliding in opposite directions. Now, remember that I mentioned that most transform faults are these little segments that occur at mid-ocean ridges. Do mid-ocean ridges normally have a lot of volcanoes, or excuse me, a lot of earthquakes? Like, were the big earthquakes in the map we saw before at the mid-ocean ridge, or were they at the subduction zones?
Subduction zones.
They were at the subduction zones. Mid-ocean ridges don't normally have a lot of earthquakes at them, but like the ridge crest example one of y'all mentioned before, the San Andreas Fault is associated with lots of big earthquakes. So why might this transform fault be associated with a lot of big earthquakes, but the ones cutting through the oceanic crust aren't? What's different about this crust versus the ocean crust?
They move differently?
It is going to cause it to move differently. The continental crust is a lot thicker and harder to break through. And if it's harder to break through, that causes stress to build up and then causes big earthquakes when the stress gives way. So the reason we have big earthquakes from the San Andreas Fault is because continental crust really kind of doesn't want to move. It's going to be very thick and two pieces of continental crust grinding past each other. It's going to create a lot of friction. build up a lot of stress compared to oceanic plates. So that's one reason why the San Andreas Fault is so weird. And when I say connector segment, one thing you'll notice is that these red stripes here are meant to show spreading centers. These are divergent plate boundaries, and you can see that there is a divergent plate boundary off the kind of in the East Pacific. That's what the East Pacific Rise is, if you ever come across that term. And there are connector segments. You'll see transform faults again because you have those same arrows connecting the Juan de Fuca Ridge, and I think this is called the Mendocino Ridge. This ridge off the coast of this spreading center, this mid-ocean ridge where oceanic crust is being made off the coast of Oregon, that is actually connected all the way to another one down here in the Gulf of California. You can see that there's a couple more of these red segments down here. So the San Andreas Fault is actually basically a giant connector segment for two ocean ridges. It's just one that happens to traverse the entire length of California, which I find kind of cool. But anybody have any questions about that before I move on? And one thing I do like about this diagram, and you'll see this when it comes back up in lab, is that you actually have all three types of plate boundaries represented. You have divergent plate boundaries at these mid-ocean ridges. You have transform boundaries connecting them, as well as, well, connecting them in the San Andreas Fault example. And then this is actually, the subduction zone is actually a convergent plate boundary. This is where this oceanic crust is subducting under the continental crust of the United States. And what are some volcanoes that people know from this area? Like Canada, Washington, Oregon. What's a big eruption that occurred in
Mount
Washington?
Whitney?
Mount Whitney is in Northern California, but yes, Mount Whitney is further south. Mount Whitney is not caused by this subduction. Mount Whitney is down here and is from when you had this down here, when you had this occurring off Southern California as well. So good example, but that's more of a geologically past one. What's a volcano that's erupted in human history, like up in the Pacific Northwest? Sorry?
Yellowstone?
Yellowstone is actually an example of a hot spot. Yellowstone geologically is caused by the same thing that causes Hawaii, where there's just, and I'll go over hotspots in a bit, but it's not caused by subduction. That's also quite a bit inland of this. So I'm talking about, can people say where the cursor is? This diagram is visible, correct?
Yes.
Okay, cool. I'm talking about like in Washington or Oregon or what's the big eruption that happened near Seattle?
Mount St. Helens.
Mount St. Helens, yes, that's quite a while ago now. I realize that's the 80s, but Mount St. Helens is caused by the subduction zone. Mount St. Helens is the magma that led to Mount St. Helens was made by subduction occurring here. So we actually have all three types of plate boundaries pretty close to us, relatively speaking, which is cool. And when I say that, so in the case of Mount Whitney, one confusing thing about plate tectonics is that where plate boundaries are now is not where they've always been. Like the Mid-Atlantic Ridge didn't always exist. There wasn't always a plate boundary there between Africa and South America, but at one point seafloor spreading began. I'm not really going to go into too much depth about how that occurs, but plate boundaries change and plate boundaries can cease to exist. And there did used to be more of this subduction off of the coast of North America. So Mount Whitney and the other Sierras are the base of a volcanic arc that used to be here in California also, but it's been replaced by the San Andreas Fault since then. And I'm not going to have a whole lot of time to go into details about that. Any other questions before I jump back to the PowerPoint? And we're almost done with the presentation. I always find that plate tectonics just kind of I linger on stuff a lot. Okay, jumping back to the presentation. I am not going to linger on this very long, but the term fracture zone refers to how there's these little places kind of farther away from the mid-ocean ridges where the crust is moving in the same direction, but I'm just mostly going to skip over that. Who was that? Who had the question about who Yellowstone? Was that Manuel? Is that your name? I'm sorry, I'm still learning people's names, but
Yeah.
okay, good, I got that right. So Yellowstone is caused by this. Actually, Yellowstone is caused by a weird case where you have volcanoes far from plate boundaries, where just out in the middle of the plate, magma just starts rising from the mantle and erupts, and the plate kind of continues to move over it. This is really deep mantle stuff. This is very deep mantle material rising and kind of operating independently of the movement of plates. It's just kind of like there's like a fissure really deep in the earth, and magma can just rise up here and comes out at this same spot, even though the plate continues to move over it. So what happens is that the plate moves and kind of drags the old volcanoes with it, and those old volcanoes die because they're not over the hotspot anymore. That's what's happening in Hawaii. That's why you have only really one active volcano in Hawaii, or a cluster of active volcanoes at one end of the island chain, because that's where there's a hotspot. And Yellowstone is also a hotspot like this, which I think is really cool. Okay, so I realized that was quite a bit of material. Some of that is kind of in here just as context, and as this is kind of applications of plate tectonics, and I'm really happy to go over any of that with people outside of this. Going over the lab itself is a two-part lab, and it's just kind of broken up to reduce the workload a little bit, I think. But for today's lab, if you, I'll open Canvas again at the end of this to show you what you should be looking at, but you'll be working on lab 02A. And there's actually 2 assignments listed for 2A, because there's the lab quiz that has most of the questions. And then there's also a place where you upload a figure that you've drawn on, where you've marked earthquakes and volcanoes on, and where you've marked different types of plate boundaries on. And I'll show you where that is in just a moment. But this lab will be due, if you don't finish this in class today, this will be due on Monday, February 8th at 11:59 p.m. And so you have quite a few resources available to you with plate tectonics. The maps I showed you, as well as a plate boundaries map, can be downloaded at the top of the Canvas assignment. This intro lecture, I'm going to upload this for reference. I'm going to upload both the recording as well as the slides themselves to Canvas, so you can use them for reference. And any notes that you have from the Geology 101 lecture will probably help you quite a bit with this. Any notes you have related to plate tectonics. And one thing I wanted to mention that I forgot to mention last week is that the Canvas site does have a previous version of the slides from when Dr. Bird taught the lecture class. So they're her slides from last term. I think she's probably made minor changes to them since, but they are on Canvas in a folder and can be used as a reference if you took the lecture before and don't have access to the slides right now, or if you just need them for any reason, I will show you where those are. So most of today's lab is questions you answer in the Lab 02A quiz. And there's an assignment for a file upload that's separate, but that's going to be graded as part of the lab. That's just because of Canvas's limitations. Dr. Bird originally just set that up as a different entity, I guess you could say, on Canvas, but it's really the same lab. So for part of the lab, you are actually drawing on a map. There is a file called Surface Relief Map of the Earth that is linked at the beginning of the Canvas lab, and I'll show you what it looks like in just a moment. And for this lab assignment, you need to either print it out and draw on it, and then subsequently scan it or take a good quality photo and upload that. Or you can download the PDF and edit it in Photoshop or in Paint or another application if that ends up being easier, because I understand access to a printer can be kind of iffy, and I only realized that this lab had a part that needs to be print off part yesterday. So if it's going to end up wasting a lot of time for you to try to scramble to print it today, do not worry about that. It's up to you whether you want to use a printer, or it's up to you whether you want to print it off and physically draw on it. I find that sometimes drawing helps me with tactile remembrance, but some people are also find that with using computer programs also. So I have no problem with people using Photoshop or Illustrator or whatever to draw lines. And the file format, that's a good question. I will double check. I am not particular about the file format. I would say PDFs are probably safest, but JPEGs are probably fine. I will double check Canvas to make sure that, to see what types of files can be accepted and if I can tweak that at all. But I am not particular about the file format. I just need to be able to see it, basically. So for part of question 1 on the lab, you actually sketch in the locations of not equations, excuse me. You actually sketch in the locations of the earthquakes based on the earthquakes map I showed you earlier. And you don't have to draw absolutely everywhere there are earthquakes. You can kind of choose to shade it, or you can draw dots. But it's kind of so that you draw in yourself where you see the earthquakes. And the surface relief map of Earth that you're going to be drawing on has the plate boundaries. It doesn't have a lot marked about the plate boundaries. It just has the plate boundaries themselves. And you can kind of start to see where the earthquakes on the earthquake map start to align with plate boundaries on the surface relief map, or not in some cases. It might be worth seeing if you spot earthquakes that are not very close to plate boundaries and mapping at least a few of those. But you definitely want to consider where the earthquakes are most clustered and kind of focus on that as much as possible. And for question 3, you actually do the exact same thing with volcanoes. And the assignment on Canvas specifies which colors you need to use. I am not that particular about what colors you use. I'm kind of keeping that as a suggestion. But if you don't have, if you say don't have all those colored pencils available, I don't necessarily care what you mark the boundaries as long as you clearly label it. And this is kind of what I'm looking for in terms of the map key or map legend you need to have for that part of the assignment. So outside of marking the earthquakes and the volcanoes, so on here I just put okay, red shading equals volcanoes, green shading equals earthquakes. Okay, cool. I was just making sure I got the colors right. And then later in the assignment, you mark different types of plate boundaries using different colors. So the map itself has just the plate boundaries shown as lines, but then you use different colored pencils to show which ones are transform boundaries, which ones are convergent boundaries, and which ones are divergent boundaries. And something I'll mention is that, yes, mid-ocean ridges do technically have both divergent and transform boundaries, but overall, they are divergent boundaries. They're dominated by divergent boundaries. The San Andreas Fault is really the big transform boundary that's out there. But again, you don't have to use these exact colors necessarily. I made it here with the colors that are listed in the Canvas version, but it needs to be clear to me what color represents which. If you can't use colors, also you can try using dots, or you can be like, divergent boundaries are dotted lines and convergent boundaries are another type of line. I'm not explaining it very well, but you can do that also if that's easier than using colors, and if you think that's going to make it easier to see. Just with I find that let me just jump out of here to briefly show you the diagram I'm talking about. So it's not down there. There we go. Rotate. Damn it, Zoom, you are getting in the way. Okay, but I'm gonna rotate this clockwise just so that it's, okay, there we go. So this is actually the plate. This is actually the map you're gonna be drawing on. So this map so I mentioned that it has some features about plate boundaries and not others. So what can you tell from this map? Like, what information does this map actually have already on it?
Where the plates
The
are.
plates.
It shows you, yeah, it shows you the boundaries of the plates. It also shows you the names of the plates. Does it show you anything about the directions of the plates?
No.
No, and that's kind of what the assignment is. You're going to be using different colored pencils to draw over areas that, oh, like I know this is a divergent. I can figure out this is a divergent plate boundary because there's another map that you look at in Canvas that does have the arrows, and you use those arrows to mark this one with which areas are convergent, which areas are divergent, and which areas are transform. And this map is also where you're going to be putting the shading that shows where there's lots of earthquakes and where there's lots of volcanoes. It's okay if it's a bit messy. I know also that like volcanoes and earthquakes are going to be in the same place sometimes, so you can kind of just do shading next to each other or put them on, or whatever works for you. But I'm happy. I will set Zoom to allow screen sharing. Well, actually, I will set Zoom to allow screen sharing if that's easier. But I can also take a look at your figures and let you know if it's what I'm looking for, or let you know if it makes sense to me. Any questions about this? This is the actual figure you'll be downloading and either printing off and drawing on, or importing to a visual editing software and kind of drawing on it using that. And once that is annotated, and you also, another thing this doesn't have a legend anywhere. And you'll put a legend like the one that I had in the last slide on, that'll show you, that will tell me or anyone else viewing the map what the colors actually mean. And in terms of where you could put that, you could hypothetically just put that in the middle of Eurasia or down at one of the corners. It doesn't really matter where that is. Or you could put it in Eastern North America, because there's not a lot of earthquakes or volcanoes there, as you'll see. Anyhow, I'm going to jump back to the presentation. We are almost done with that. So thank you for being patient with this. And I also will acknowledge that I'm still kind of, since this is my first time teaching here, I've taught plate tectonics before, but I'm still learning how AVC does it and getting a sense of what is covered in the lecture class. So there may be times when I mention something that you're like, what? Because it wasn't mentioned in lecture. If that doesn't really come up on the lab, don't worry about it. I'm kind of working on filtering that out still and targeting this. But hopefully that was interesting. So next week, I will say, the lab that you're working on today is due next Monday. There is also a short quiz on the Maps lab that is also due on Monday, February 1st. And that is visible on campus, on Canvas under the quizzes tab. And I'm actually going to jump one more time out of here and go back to Canvas to show you just a couple of things I mentioned before I end the presentation. I had it open somewhere else, but I will just open it here. My ABC home.
Sorry, that quiz was due on February 1st.
So this is not the lab that I had you do last week. There's like another kind of follow-up quiz that comes along with it that's due on the 8th.
Okay.
So let me show you what I'm talking about. I'm sorry, I was just navigating my way back over to Canvas. So let me actually put this in student view. So this actually looks like, okay, it's in student view now. So this should be like what you should be able to see. So I jump over to assignments, and actually I didn't notice this because it doesn't show me this in teacher view, but upcoming assignments kind of lists assignments by when they're due. So you can see here, this is the lab you're working on today, Lab 02A, Plate Tectonics Part 1. And then due February 8th is also this Lab 01 Maps quiz. I am realizing this looks quite different in student view than in teacher view. So I will try to see what I can do about that. But aside from the labs, the only work for this class is going to be the final exam near the end of the term. And then there are a number of small quizzes that are meant to be review quizzes for the previous lab. They're short, like 10 questions at most. And there is one based on the material we covered last week for the Maps lab that is due next Monday at 11:59 p.m. So that's a short quiz that you have a 30-minute time limit for, and you are actually completely able to look. You can absolutely reference the Maps lab while looking at this. It's meant to be as you can use Labs 01 as well as the textbook or in stuff in Canvas. You're not really supposed to talk to your friends about it, but it's kind of just a, have you retained the basic stuff we covered last week? Do you still like, do you find it easier, like now that when you take this quiz, do you find it easier or harder to answer questions about the relative sizes of continents or distortion or whatever? The questions are going to be really similar to what was in lab last week. So it's not going to be drastically different material, but you do want to make sure that you do this before next week. And that is something you want to keep an eye on. In student view, this actually, oh, okay, you can do it. You can do show by type also. So this is actually kind of what I expected to see. If you click on show by type, that lists the lab assignments. So this upload window here is actually what you're going to be putting your completed drawing in. That's how you're going to upload your completed map drawing. And then if you scroll down here, lab quizzes, that's where these are. So don't worry about this one yet. After we finish plate tectonics, there'll be another quiz on that. But this Lab 01 maps quiz is the one I want you to finish for next week. Does that make a little more sense?
Yes.
Yeah.
Yes.
Okay, cool. Last thing I want to mention is that I mentioned earlier that that somewhere in here there are lectures from previously, and now I cannot find that, but I will make sure that is visible. So I am going to stop recording in a moment and stop the presentation. So I'll be around to answer questions about this. I'm happy to go over parts of the presentation again or answer other questions about plate tectonics. And I'm going to open the rest of the time up for work time. So thank you all for listening and for your questions. And I'm going to stop the recording now.